Good afternoon, everyone, and welcome to our webinar, Finding Downtime You Can Fix, Identifying Opportunities, Analyzing Data, and Understanding the Impact of Process Changes on Your Manufacturing Operations. Today, we will look at the different ways to identify downtimes within your factory that are within your control. Whether it be man, machine, or method, there is always improvement hidden in the details. Today's agenda will be fairly straightforward. I'll introduce myself a little further, go through the goals for today, a bit of background, and from there we will dive right into how to find downtime in your factory. This presentation will focus on different tools for identifying and validating your assumptions, which will ultimately guide you on where to invest your resources for the greatest return. A little about myself. My name is Lucas Walker. I am a field application specialist at MAJiK Systems. I focus on teaching clients how to get the most from their data that is revealed when utilizing MAJiK's manufacturing execution system to monitor, analyze, and optimize production in their factories. Generally, an MES provides the right information at the right time to show manufacturing decision makers how the current conditions on their plant floor can be optimized to improve production output. While there are different solutions for an MES on the market, not all are created equal. MAJiK differentiates itself as an MES by connecting directly to the capital equipment and other factory information systems by using the native protocols of data sources such as PLCs, CNC controls, HMIs, SCADA, and ERP systems. That means no downtime and no additional third-party hardware during installation. I also think that we have the best user interface and data visualizations in the industry for root causing downtime, identifying causes of scrap, and matching production against process data. However, luckily for all of you, in my previous role as a process engineer at Toyota Motor Manufacturing Canada, I did all of this work the hard way. And so during today's presentation, I will walk us through both methods of practice to ensure that even if you don't have an MES, you can use this as a guide to perform some of the same analysis in your factory setting. So for today's goals. Today, my goal is to have each and every one of you go out to your factory floor and take a second look at the areas that are ripe for improvement. By the end of this webinar, you'll likely have 3 or more areas that you've identified as potential processes to improve. I will cover different methods of analyzing these processes to ensure that you will find the improvement you believe is there. We'll also cover some of the critical steps to ensure that these changes are sustained and maintained. Far too often you'll see a change made, and it may last a few weeks or months, but in times, things will return to their previous state and nobody quite understands why they aren't seeing the improvement they once did. With regards to questions for today, I'd ask that you email them either during the presentation or afterwards to lwalker@majik.io to ensure that we can maximize the time that we have today, as well as to ensure that questions are given the adequate amount of thought and insight that may not be possible during the webinar. So let's take a moment to step back and look at the big picture of what it is we're looking at today and address each of the points listed here. What are necessary activities? They are cleaning, sanitizing, mold changes, process changeovers, you name it. Our goal is to reduce the impact of these necessary activities. How do we do this? It requires a deep understanding of the process or the activity itself. What do we consider acceptable? Obviously, we'd like all processes to be instant and use the least amount of time possible. However, we need to understand what is acceptable to ensure that we're not spending more time and money than is necessary to try and achieve the impossible. Do you know what is happening on your factory floor? This may be one of the biggest questions to ask when trying to identify where improvement can be made. We need to understand where the time goes to ensure that we know where to focus. And lastly, what is it we can control? If we don't understand what we can control, then we'll constantly spin our wheels in search of improvement that may not actually exist. Okay, so how do we identify opportunity? Above, we've identified some of the processes that happen daily, but we should also evaluate which of these processes are considered critical or unavoidable to ensure that we are in fact having them take place as needed. If we are focusing on tasks that are optional or intermittent, then we won't see the same sustained gains in productivity. As a primer, and to invoke some critical thinking, let's take a look at an everyday example from our personal lives outside the factory that would be comparable to what we are trying to solve on the factory floor. I want you to think of your morning schedule and what it entails. For some reason, it never seems to take the same amount of time to accomplish. If we are trying to optimize it, where do we look? Let's take a second to think about that. You likely thought of your daily commute. However, this isn't the type of situation we're looking for. The issue with trying to use your commute as an example is that you've likely already optimized it. All the issues that cause you to fluctuate, such as red lights, accidents, traffic, and whatnot, are all out of your control. You've probably already spent time determining the best route, the optimal time to leave the house, and anything else that you can control. A more appropriate task to evaluate during that morning routine would be before you leave the house. This type of routine is something that we find ourselves treating a little bit too liberally, as we feel it doesn't directly affect the rest of the day. These include things such as hitting the snooze button once, twice, or in some cases 7 times. You may flip-flop on what it is you want to make for breakfast, or you decide that stopping at Tim's is a better idea than making coffee at home. All of these items can greatly affect the rest of your day, but are seemingly flexible in spite of this fact. Today we'll break down the routines of our workplace and try to understand why we treat those differently and what inefficiencies lie within them. So, once we've identified which processes are unavoidable, we need to look for processes that are not yet optimized. Here we can see the tracking for the changeover of a machine. We can see that this setup time varies quite greatly in its duration, lasting anywhere from 25 seconds to as much as 16 minutes. Note that these setup times are for the same product. We are comparing like variables or apples to apples. This type of variability in a process should immediately raise red flags for the process engineer, continuous improvement manager, or production manager, as it shows that there's a problem with the process. Now, when I'm saying problem, I'm not saying that the setup isn't being complete or that it's done improperly. I'm defining a problem as a scenario in which a process or procedure that should be consistent is not being performed as expected. This type of variability also tells me that the process has not been optimized around a certain expected time. We see very little repeat durations in this process snapshot. If the graph showed a fairly steady trend with outliers, it'd be far less concerning. Soon we will look at where to find this data and how to make it presentable. But first, we're going to go through a few short definitions to ensure that we are all on the same page. Duration. When I'm referring to duration, I'm generally talking about the total duration for a particular fault over time, essentially the sum of all those faults that have occurred within a given time period, whether it be 6 months, 12 months, or simply 1 day. For the term instances, I'm referring to the total number of individual occurrences of a particular fault over that same given time frame. It can be used interchangeably with frequency of a fault, as when we discuss frequency, we are typically referring to the number of instances that occur for that fault. The next is mean time to repair. This is the average time it takes for a particular process or to repair a machine that has suffered a breakdown. Typically, we only associate MTTR with breakdown situations. However, they're an excellent method of measuring the performance of your mandatory downtimes, those that we've already talked about, such as cleaning or mold changes. This metric is very useful in telling us whether or not our process is optimized, because we're looking to see that it's been done the same way each and every time. Next, we will also look at the mean time between failure. Mean time between failure is a very useful metric for understanding a couple different things. In breakdowns, it may indicate the upcoming failure of a motor or gear as the frequency of the downtime increases and the fault occurs more often. But in the context of today's topic, it indicates our measure of consistency. If we are consistent in how our processes are being performed, both in MTTR and MTBF, it tells us that we have a very stable process. So now, let's dive into how to find and obtain this type of data. First, I'll show you using an MES. Here's an instance of MAJiK Systems' web-based MES solution. From this first equipment module, you can see that you have your equipment utilization on the left side, as well as you have work orders shown on the right side, both in progress, past, and upcoming. We have a quick snapshot of what downtime has taken place over the last 8 hours, 3 days, 2 weeks. And we also have how our current production is performing. Now, if I'm utilizing this screen to find my downtime, I may fall a little bit short. You can see if I dive into my machine changeover, I get a couple instances over the last 8 hours. Or I could go back over 2 weeks and look at the same machine changeover time and see that there is some fluctuation within it. Now, this may be good for looking at the last couple of weeks to try and understand where there's been a problem or what type of issues we may be having. But if I'm trying to find where I can find consistent, changeable downtime, I'm going to want to dig a little bit deeper. In order to do so, you can go into your MES, and typically you'll have a downtime analysis tool. In this case, I'll go to the MAJiK Systems tool. So within this module, my data is already sorted for me into groups by equipment line. This gives me a very quick and simple visual of where I'm seeing any problems. I can filter by different parameters down the left side, whether it's the machine grouping, machines themselves, types of downtime, or the downtime itself, as well as I can see by color coding what exactly I'm working with right up front. I can also set notifications for downtime within here if I'm so inclined, as well as use a few more in-depth analysis metrics that are calculated in my tooltips when I hover over. So when I'm looking at this downtime, I can see from the color coding in planned that my track line has the most planned downtime. When I compare the total number of instances, I have 6 hours over the course of 42 occurrences. Compared to my A918, I've only got 49 occurrences for 4 hours. This tells me I want to dive in and look at my track line. So let's drill down by the type of equipment. So within that track line, I can see that my L1 line, or piece of machinery, has the most planned downtime. I can quickly and easily click and drill down into this reason code and see that within all my different types, machine changeover is my #1 planned downtime. If I go a little bit further, I can see that, sorry, I need to navigate my way back, but let's do it quick and easy. There we go. So again, planned downtime within my track line is fairly easy to get back to if I do find myself going out of rye. So let's look at the planned downtime itself by type and equipment. So we can see on L1, our planned downtime is our #1 issue. Now, if I want to really see what's going on, I can select all over here and see that down in the left-hand corner, only machine changeover time is selected. That tells me that I have over 3 hours of machine changeover time on this L1 line alone. Now, if I want to compare that to all of my machines, I can unselect this and check out my machine changeover time for every single machine. What this is telling me is that I've reconfirmed that the L1 line is my #1 problem, even when comparing it to the other machines, and it tells me that I'm on the right track. When we take a quick look below, you can see that for each of these machines, the duration for each fault varies quite a bit, anywhere from a few seconds to 18 minutes and more. This tells me that we found a process that has a large degree of variation in the MTTR, and it tells me that this is where I should look. With this type of information, I can now go down to the factory floor and get a look for myself. So when we look, we do see that the differences between machines is not very significant. But over time, this accumulates. Because you can see here, we've only selected a 1-week span, we know that this is really not a major impact, but over months and months and potentially over the entire year, this adds up to quite a bit of significant downtime. And from here, I could keep digging into this using the MAJiK MES system, but I think you probably get the idea. Instead, I'm going to export the data and walk through some more in-depth analysis in Excel to sort of give you the nuts and bolts behind this type of analysis. You can see in the chart below, I've already got it filtered, and from there, I can export to CSV and work through it that way. If you don't currently have an MES, you're probably using Excel to record most of this downtime anyways, so hopefully the next few steps will be very useful for everyone. If you need help getting a data set together to do downtime analysis on your own factory, please contact me after, and we can either do it through our downtime analysis tool or utilizing Excel itself. So, in order to manage large sets of data, we need to use a pivot table. We're going to quickly run through how to create a pivot table in Excel, just to ensure that everybody's on the same page. Of course, here we go. I'll just pull up a file for us, one moment. There we go. Technology always works when you want it to. So in order to create a pivot table, what we first do is export all of our data, and you can see here that we've actually got quite a large set of data. It's probably 30 to 40,000 rows. But it's already been sorted into dates, the fault type, the fault name, as well as durations. Now, because this data came directly from the machines, you'll see that the duration is sorted into milliseconds. This means we have as accurate as information as we can get. Personally, I like to break it down into minutes and hours as well. This lets me know that I can dig a little deeper if needed, but also get a good macro picture of the situation. So in order to create a pivot table, it's pretty simple. You simply select all of your data, move to the Insert tab, and click Pivot Table. I always confirm that I've got the proper range of data that I need, and then I hit OK. So from here, we want to look at filling this information with our duration. In this case, I'm going to use the duration in minutes. To set this up is pretty simple. I just click, and now I've got the total sum of all the durations for those downtimes from my data set. Obviously, this isn't too helpful as it is, so I want to sort it by fault name. One quick click, and now I've got an entire table by fault name with the total duration of all of these downtimes. In order to properly understand what's going on my factory floor, I still need to break this down into 2 additional tables. So in order to do that is quite simple. Just make a quick copy of the table. In this case, I'll make 2. There we go. Now, my second table, what I want to be looking at is the total count of occurrences of each of these downtimes. This will let me know how often it's happening and whether or not I should be putting my resources and effort into it. In order to change it to a count, it's very easy. A quick right click, go to your field settings, and change it to count. It's that easy. So now I can see that I've had 1,500 minutes for abnormal oxygen faults occurring from a total of 46 different occurrences. If I carry that one more time through, my last table that I want to use, and arguably one of the more important ones, is my MTTR. MTTR is really just evaluated by looking at the average. So once again, right-click, pull up my field settings, and go to my average. I like to clean up my data a little bit because I don't like too many decimal places. Here we go. So now when we look at this again, I can see I've had over 1,500 minutes for an abnormal oxygen fault. It's occurred 46 times, and the average fault will last a little over half an hour. If we want to, from within here, we can sort it from largest to smallest to see which faults cause us the most problems, which ones occur the most often, and typically the most important, which one has caused us the most downtime to date. In this case, you can see that sealer head cleaning is something that has caused us over 90,000 minutes of downtime, has occurred almost 4,000 times. But when we look at the actual duration of the fault itself, or its MTTR, it only lasts approximately 24.3 minutes. So this is what I would call a micro stoppage, or it's one of the ones that sort of nickel and dimes you for downtime and adds up over time. The importance of this last piece is that because it's a shorter MTTR, we may not immediately look to it for improvement. And this is kind of what we're going to go into next to understand why I'm going through this and why we need to look here. So let's continue on. Like I mentioned, if you don't have an MES with the capability to break down your stoppages as we did, or if you don't have an MES, this is where Excel comes into play. These tables should look familiar since we've already done this. If you still need more insight on how to use pivot tables, there's plenty of excellent online tutorials you can do, or alternatively, feel free to email me and I'd gladly work with you and your data to set something up. Now, when I'm looking at my data and trying to determine which downtime to assign my resources to that will have the highest impact, there are 3 key things that I'm looking for. The first is total duration in the top table. The second is instance, or the frequency. And the last one is the MTTR. Specifically, I'm looking for variation in the MTTR, either by machine, as it's been sorted in this table, or a month-over-month basis. So let's take a look at this data set. you'll see that there's 3 circles around the same downtime in each table. What's interesting to note here is that while cleaning is not necessarily the #1 item in total duration, that goes to the honor of scheduled PMs, it does have the highest frequency, or it occurs the most times. What's most interesting to note here, though, is that it has a very high variation in MTTR between the different machines, indicating to me that there's variability within the process. Myself, I've been trained to spot these types of downtimes that are ripe for improvement over years of habitual practice, but there are alternative methods to helping you select which ones to look for. It's not exactly a perfect science, and there is some trial and error, but you will eventually find a method that works best for you. An alternative to what we're doing here today would be to design a weight system, and then this will help you select which downtime to attack and reduce. In this case, weighting duration, instance, and MTTR, and then selecting your #1 downtime to work on. Just one thing to keep in mind if you are going to go that route is that a large MTTR does not necessarily indicate that there's lots of room for improvement or that there's a problem. It's the variability within that MTTR that we're looking for. And now we're going to dive into why. If we have a process that's optimized around a certain time, then we should take a look at how consistent that process is around the expectations. In this particular example for a cleaning process, we can see that it's centered around approximately 25-26 minutes, but it has a large distribution of times around that expectation, anywhere from as little as 1 minute to over 60 minutes. This indicates that there is a large variability in the duration of this process. This is what is so important, because it tells us that we are missing either an opportunity to reduce the expected duration or that we're losing time somewhere in the details of the process. If we were to choose a very stable process, one that has a tight distribution around its norm, then there's going to be very little room for improvement. If we were to look back at our daily routine example, this could be compared to the process of brushing our teeth. For some of us, we know that we should be doing that for a full 2 minutes, and we're very diligent and hold ourselves to it. However, some people may fluctuate in that time. So for some, you may see a large room for improvement. Others, there's not much we can change. Once we've identified a process and the right downtime to tackle, we want to look at how to achieve progress. So, regardless of whether we started in an MES or we just had our raw data in Excel, we're now at essentially the same point where you're looking at these types of tools to make progress. #1, as I mentioned, is we are looking for variation. A stable process can be improved but requires far more work. You need to look for processes that have a large variation in their duration. The next is benchmarking. The most effective way to make progress in your plant is to find a similar process that is outperforming the one you're trying to improve and benchmark it. This can be done in a variety of ways, one of which we're going to talk about shortly. The last is to standardize and yokoten. Once you've established that the benchmark is effective and you can apply that to a similar machine, the next step is to standardize and yokoten. Yokoten is the Japanese term for sharing across all of your plant or your factory. It essentially means you need to take the lessons that you have learned in one area and share and apply that to other processes that can benefit. This is how improvement can be easily scaled, replicated, and sped up when making change on the factory floor. So let's dive into each one of these points. How do we achieve process? When we look at variation, we need to look to understand where improvement can be made. This goes back to focusing on the variation in mean time to repair, just as we pointed out in that earlier table for cleaning. When you found a large variation in MTTR for a frequently occurring downtime, it's costing you productivity, and it tells us that we can do further analysis into this process. In order to understand how to improve that process, you must first observe it and document all the necessary steps that are required to complete the process. Once these have been recorded, you can start to understand if these smaller microprocesses are performing as they should. When we look at this table here, it tells us that we need to do a time study. So how do we perform a time study? This is a typical example of a good process time study. What I've done here is actually gone through some previous experience and looked at what has to be done when you're cleaning an injection molding machine. You can see in the list of steps that it goes right down to some of the very finite things, such as entering the machine, applying your lockout lock, or simply turning it off. More often than not, you can do these with very simple tools. Realistically, all you need is a stopwatch and a clipboard. If you don't know what the finite steps are for your process, then take a blank sheet and your stopwatch and go down to the process. Make sure you choose your best performing machine so that you can establish what your target will be as we move into the benchmarking phase. As you observe the team member performing each step, make a quick note of the actions being completed, as well as the time it takes to do so. This whole concept of going to the floor and seeing what is happening is referred to as Genchi Genbutsu for the Japanese. It is the concept of taking the data you have observed in the analysis portion of your process and then going to the process to understand whether it's the cause or if it's actually reality. Once we've established a best process and we've documented it like we have here, we should move on to our benchmarking phase. Benchmarking is by far the most effective and fastest way to identify where you have an underperforming process. If we look at the table above, you can see that machines 1, 3, 4, and 5 all have an average MTTR of approximately 20 minutes, whereas the other 4 machines are almost twice that. If we go back to our first time study, one of those first 4 machines, 1, 3, 4, and 5, would make an excellent starting point to do our initial evaluation. We can use one of these as a benchmark to which we evaluate and improve the other machines. If you can use the 4 better performing machines as a benchmark, you can go back and evaluate exactly what's happening at each of the individual underperforming machines. In order to do this, you may have guessed it, another time study is in order. So, when we take a bad process and do a time study, again, we're breaking it down into its individual steps, and this is where it becomes clear that we are losing time when compared to the benchmark. We can see here for this process that it takes significantly longer in the individual steps for cleaning each injection head. Beyond that point, they're actually fairly similar. This is extremely useful because now it means that we can focus our resources on why this particular machine, or potentially the team member, needs so much longer to clean the injection heads. Rather than trying to fix the entire process as a single entity and wasting resources in areas that may not be necessary, we can now not only be more effective, but also reduce the countermeasure time required to ensure that this process is brought up to the standard. Lastly, we want to standardize and yokoten. Once you understand what your best practice is, you have to make it the standard. We should be able to reevaluate our once poorly performing process and see a clearly defined average or close to the original average with maybe a slight variation around that. Standardization is also the key step in ensuring your improvements are maintained. If we don't standardize the change that was made, it quickly falls off and we go back to our old ways. This is also now gives us a level playing field from which to evaluate all the machines that are running with this standard. There are different strategies for standardizing on your factory floor. I'll quickly show you some that can be done using an MES to give you some instant feedback and let you know how your process is performing to its standard. So let's dive back into the MAJiK Systems MES. So within the MES itself, there's multiple ways to set up different indicators for how you're performing. When you're initially trying to monitor the progress of a recently changed process, you can actually set up custom notifications to email you. So in the case of my machine changeover time, which we see here, I could set it up so that I get either a text message or an email anytime that exceeds my new standard time. If I have it just for a specific machine, I can set it up that way too. This is a quick way to keep a very close eye on the process so that I can understand that the changes I've made are actually sustainable. There's also ways to change your run rates so that you know that if you've made improvements, you expect a certain run rate, you can now evaluate those themselves. You can simply pull up the part you're trying to make and adjust the run rate to the new standard. The other major benefit that you get from the MES is that you can quickly go to shift reports and compare how you did from previous days. This helps to build consensus within the factory floor, and it also lets people know how you're doing with progress and how the changes you've made are having an impact. In this case, I could pull up my total shift from Monday and then evaluate what my downtimes were over that day. In this instance, you can actually see that I was having issues on my night shift with the machine changeover, as it was taking almost twice as long as the other 2 shifts to complete. This is a great way to once again go back and check to make sure that the changes you've made are actually being sustained. Without an MES, all of this can still be done, either with checking in on the process, assigning personnel to the station to monitor at all times, or holding weekly, daily, or monthly meetings. It doesn't have the same immediate response time as you would with an MES, but it's progress, and that's the most important part. So let's put this all together to understand exactly what it means. Let's go back to this table and understand the impact of what these changes can have. If we were to reduce the time taken for underperforming machines and make that equal to 20 minutes, the 4 benchmark machines, then we can evaluate what impact this has on our operations. To understand the impact, we take the difference, in this case 8 to 18 minutes for those 4 machines, then multiply it by the occurrences that we have already had to date. This is going to allow us to evaluate how much time we could have saved had we benchmarked and made them all performing at the standard. When we add these 4 machines up, it's a pretty staggering number. A little over 8,000 minutes of downtime could have been avoided. If we want to put that in a little bit more realistic terms, that's 134 hours, or a little over 3 weeks production. This right here is how we justify the amount of time and effort it takes to go into finding these improvable processes. And this is where an MES with the proper tools that can help you break down time, reduce time spent on analysis, and monitor your adherence can also pay huge dividends. This is essentially where the continuous improvement manager, production manager, or the process engineer is paying for their own salary. So let's briefly take a look at some industrial case studies. We'll touch on mold changes, material or job setup changeovers, as well as some cleaning and sanitizing within the bottling industry. So let's take a case study within the injection molding industry. What's our problem? We know that operators require a new mold for a production run, and each of these molds typically need to be preheated before the changeover can happen. What we found was that the operator was continuously waiting on the heat up time because the mold process was started too late. So in order to fix this, you break down the process into its finite elements. And you can see that occasionally, or more often than not, the heat up time is not actually being included in this mold change procedure. When you show the operator the impact of the heat times, it allows them to understand the importance of making sure that that mold is staged prior to the actual change procedure. If you're lucky enough to have an MES with notifications, you could set it up so that it will either email or text message somebody with 30 minutes left in the production run, allowing them more than enough time to go and grab the mold, get it onto the heating table, and allow it to preheat prior to the change. This means that when it's time to change, you can do it immediately, rather than trying to wait for the heat up time and then do a mold change. You've probably read the summary already, but I'll go through it once more. By ensuring that operators understand the impact that their role plays on the mold change times, they can be proactive in starting mold heat up and avoiding costly delays. Again, with everything we're doing here, it's always about being proactive. Let's look at a custom CNC shop. So the situation, and it's probably one that many of you have seen, is that there's a job shop that runs multiple jobs throughout a day with multiple CNC cutters, which means that they have to do many machine changeovers as well as material changes. Now the operators found that they were utilizing this changeover time to take a quick 5-minute break, maybe 7 minutes, because their thought process was that because it was happening during the downtime, they weren't affecting the machines. However, this additional downtime during the setup and changeover could actually cost the company hours of overtime every week. So by utilizing the Genshik and Butsu, or the go and see principle, to go to see what's happening during the setup, supervisors realized that the operators were taking their breaks at this time. When they did a time study, they found that all things considered, the rest of the process was very equal. It was simply this break that was causing them to go past their expected time. When the team members were showed the impact of their breaks on the company and the total time, it became clear that setup time was crucial to their success. So again, as a summary, when they could see the impact of the actions they were taking, they began taking breaks during the machine operation time and using offline manpower to reduce that impact. This ensures that there's maximum uptime and minimal setup and downtime. And one final case study, we're referring to the bottling industry and cleaning and sanitizing. So in the food industry in general, there's always daily sanitizing of equipment to prevent contamination. However, with the company we were looking at, these times were largely variable day to day. The risk is that poor sanitation can lead to either a bad product or legal repercussions in the worst case scenarios. So as a result, the team members and the supervisors went to the line and did a time study to try and understand what was happening during their sanitation. They found that the sanitation contact time itself was adequate, but what they were fluctuating on was their rinse times. It was inconsistent, causing either too much material being wasted or some sort of bleed through of the sanitation material into the product. By identifying this and knowing that their sanitation process was safe, but it was the rinse that needed improvement, they were able to reduce the overall process duration and ensure that there was still no risk of bad product. So again, it's going back to identifying those micro processes that happen within a macro process, and trying to understand where it is you're actually losing your time. So let's do a quick recap on everything we've touched on today. One of, if probably the most important takeaway from today, is to look for processes that are internally influenced. Just like we talked about with our morning routine example, there's no point in trying to optimize something that you have no control over. Once you've identified these processes, take a look to see if there are similar machines or areas that are doing the same thing, and see if you can benchmark those processes as a starting point. This will not only save you time, but ultimately money. Once these changes are made, you have to track your process. This is something that I cannot stress enough. Without confirming the impact that your changes have made, you'll never truly know if that new process is either performing at, above, or below your expectation after benchmarking. And if you're lucky, it may even now outperform the benchmark, and now your whole improvement cycle starts again. After you've established that your changes are effective, standardization and standardizing the new process as much as possible allows you to break it down into finite elements that can be evaluated. These finite elements are what give us the ability to have a quick and very effective sanity check when you're looking in on the process. By the time you've finished all of these steps, you'll likely find that as one process begins to improve, it will cause problems in other areas to surface. This becomes the basis for continuous improvement. With the tools and tips that we've covered here today, I'm confident that you'll be capable of affecting real, positive change on your factory floor. And as you can see here today, I've shown why I would always recommend using an MES to help you improve your factory performance. But on that same note, my role within MAJiK is to integrate the new MES technology with the classic tools already in place on the factory floor. This includes time studies, benchmarking, Yoga 10, and all the other concepts that we covered here today. That's why I wanted to take you so thoroughly through the offline toolkit that can be a great starting point for you to go and look at your factory with, even this afternoon. When you can combine those powerful offline tools with the quick data assessment and visualization of an MES, you'll become even more effective than you thought you'd imagine. So I'd like to thank you for your time today, and it looks like we've got a few minutes to spare, so I'll actually be taking a question from our email. So looking at it, it looks like somebody's asked if I can go back over a few of the Japanese terms that were used in this because they'd like to keep them for their own records. So the first one is Yoga 10. We've probably heard this since we were 3, but it essentially comes down to sharing is caring. If you have knowledge, you need to share it with the rest of the factory or your company to ensure that what you're doing right, or maybe what you're doing wrong, is being shared with the other people in your factory, in your company, so that total learning can take place. The second one was Genshi Kenbutsu. To me, this is probably one of the key terms and the key mindsets that you have to take on. Again, it is the concept of go and see the factory floor. Essentially, what it's telling us is that data alone doesn't solve our problems. If we were to take a look at the CNC case study that we went through earlier, if you were only to look at the data coming from that and see that your setup times were excessive, you would assume that something is wrong with the machines and their setup. You'd probably try and invest maybe hundreds of thousands of dollars in automating every single one of those machines. But with a quick Genshi Genbutsu going to see the process, it was pretty easy to find that it was more of a man problem than it was a machine problem, and that the countermeasure was not only very effective, but free. The argument to the flip side of this would be that if I can just go and find out what my problems are, why should I get my data? Well, this comes down to sharpening your axe. Walking around your factory floor looking for problems is a style of management by walking around. However, it's not necessarily the most effective way of finding areas for improvement. So why do we need the data? It means that we can go through the data and very effectively and very quickly go to the factory floor and see where we can affect a quick and positive change. Again, if there's any more questions for today, please don't hesitate to email myself at lwalker@majik.io or the team at MAJiK Systems, and we'd be more than happy to go through the data sets you have or identify any opportunities in your factory. I'd like to thank you again for your time today, and I hope that there is some takeaways that you've got from today. And again, look for the recording to come out in the near future. Thank you.